Hello everyone. Hello. So let me start the class today. So today we're gonna study about the reinforcement learning only in English because last time I posted the reinforcement learning lecture last time, but it was purely in Korean. That's why it was not helpful at all for international students. That's why today we're gonna study about the reinforcement learning. Can you hear me? Can you hear me? Can you hear me? Hello? 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 Can you hear me? It's good? Thank you. So last time, so maybe 2 or 3 weeks ago, I posted a reinforcement learning class only in Korean at first for the recorded video. After the distribution last week, we studied about the reinforcement learning that also only for the conventional algorithm. I mean the Markov decision process or Q-running or something like that. But last time we could not cover the deep learning based reinforcement learning solution procedure. That's why today I would like to introduce deep learning based reinforcement learning only in English. Okay. So Korean lectures is already distributed. That's why you guys have the lecture videos. So it will be helpful for Korean students, but this lecture is only for the international students. But if you are Korean and if you want to study about this one in English as well, then you can stay here. You can feel free to come here because it's your class, okay? So let me start the class by sharing our lecture slide. But before starting, let me have just 1 or 2 minutes. I need to upload my video recording for our previous class. That's why just wait 1 minute. Then we can start the class immediately, okay? So here we need to, so just wait 1 minute, please. Here. Okay. 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 Let me wait, please. I'm a little bit confused about the Okay, let's start the class here. So in graduate school, the reinforcement learning, I'm not sure where we are now, but let me start the class from here, okay? Let me share our screen here. So here, let me start with the, so before starting here, let me share, I'm so sorry. So I have several reinforcement learning lecture notes. That's why I'm a little bit confused how we need to share. But let me explain the other topics with this slide. This can be also shared with you guys soon. So up to here. So when you look at this slide, that is also very similar to our previous ones. So here we have some, we already covered some introduction, and we already covered what would be the potential applications for reinforcement learning. And then we studied about the Markov decision process last time. So the chapter 1 was absolutely covered in our previous classes. From now on, let me start with this one. Let me share this lecture slide in our chatting box as well. So here, let me share this one. So this is the lecture note for today's class. So when you look at the Kakao chatting box, you can download this PDF as well. I will upload this one to our Blackboard as well soon. So when you look at this one, for the second part, we're gonna study about deep reinforcement learning theory. And then we will gonna study about deep neural network summary. And then we will gonna see how this deep learning architecture can be used for the reinforcement learning computation procedure. So this is kind of the toy model for neural network architecture. When you look at this neural network architecture, you can see some input state in neural network. So in this neural network, you have two hidden layers, you have only one output layer, you have input which has three sizes. That's why you have three circles over here. And then this three size vector is coming to the hidden layer first. And then this is a 1/3 matrix. That's why you have to multiply with the 3/1 in order to make only one single data. And then you have the multiplication with 1/3 and 3/1. That's why you have only one single result. And then that result will be added up with this bias. And then this will make this only one circle here. So this one is multiplied with this one. And then this return value is only one single data and added up with bias, and then it will be computed with the activation function, and then you get this result. And in a similar computation, this result is this one, this result is this one, the last one's result is this one. Okay, and then if in second hidden layer, the four size vector is coming. That's why you have 4/1 here. And then you have only one single data by doing the multiplication with this vector and this vector, because they are 1/4 and this is 4/1. And then based on this only one single result, you will add up with this one bias and you will get one data, and then you will take the activation function for that. And then that result will be this first element. And this result will be the second element. This result will be the third element. This result will be the fourth element. Okay. And then you have only one single vector again. And then that will go to the output layer. You know, output layer, since the incoming data is has four size, that's why you have a 4/1 matrix here in order to do the linear combination. And then you have one data, and that data will be added up with this bias. And then you take the activation function on top of that. Okay. And then one data is coming out. That will be our result over there. Then what we have to understand why we have to use the neural network here. So when you look at this slide, in the left-hand side, you're gonna see the interpolation. In the right-hand side, you're gonna see the linear regression. When you look at this figure, you see why they are different to each other. In the interpolation, the curve may not be linear at all. However, the curve should go through every single sample data. So it has to pass by the first, second, and third sample data. And in this case, right-hand side, even though you have a lot of sample data over here, you have to calculate only one single linear curve that has the minimum difference from the others. Okay. Then why we have to study this one? So in here, our interest is interpolation. Okay. And then if three data are existing on top of this curve, and they are goes through just like that. Okay. And then you have this one and this, then you understand that there exists a single second order polynomial equation that can go through this given three data. And then you have this kinds of the second order polynomial equation. And then you have 1.1, 10, 2, 15, 3, 40. You have these three sample data. That's why you have to put the result into here. 1, 10, 2, 15, 3, 40. You have to put these three data into here, and then you can derive three equations by solving these three equations in a system, and then you can get the solutions for these blue ones. Blue means the variables. That's why you can get the result of these blue ones. Okay, and then you can finalize this equation. That is our interpolation procedure with the polynomials. So why we are studying about this one in neural network class? Because neural network function is almost similar to our interpolation procedure. So when you look at this one, as we know how to compute this neural network architecture, suppose that you have an input here, you have an output here. When you have an input, for the first hidden layer, it should be multiplied with the weight factor and then plus bias and activation function. And that is the result of the first hidden layer. And then you have to multiply with the second hidden layer's weight, second hidden layer bias addition, and then you have activation function. And that would be the result of the second hidden layer. And then for the output layer, you are multiplying with the weight factor and you are adding with the bias. And then finally, you are taking the activation function in the end. Then this equation is very similar to this neural network architecture computation. Okay. Okay. So here, suppose that when you look at this one, so you want to find this equation by putting a lot of data in X and Y. In X and Y, you will put a lot of data. Then you have to find these blue ones. You have to find the weight vectors in here and here. That's why your purpose is finding the blue characters. Those are parameters to train based on the training data X and Y. That's why you put a lot of X and Y over there, and then you will get the result of the parameters, okay? So wait a minute, please. There are noise out of So there is noise in the second floor of the engineering building. I just want to make sure what's happening out there. There are some constructions out there. That's why we have some noise. So anyway, let me come back to this lecture. So here we made this equation. So this figure is exactly the same with this equation. By putting a lot of data in X and Y, we have to find these values. That is called training, right? That's why this kinds of the functional approximation procedure is equivalent to the neural network training. Okay, that's why we are doing the functional approximation. But here, suppose that you are putting a lot of Go playing state. Go playing state here. You are putting a lot of corresponding actions here. Can you hear the construction sound over there? No, it's very noisy. So here you can see that you are putting a lot of Go playing state here. You are putting a lot of actions here. Then you can find the parameters that can derive the actions based on this state. Okay. Let me check over there. So the construction noise is very serious. That's why, so sorry about that. I just want to make sure there is something wrong or not. So let me come back here. So here we have one equation that is derived from this neural network architecture, and you put a lot of Go playing state here. you put a lot of actions here, and then you have to train these ones. Once you are done for the training, you will put new go play state here, then you can derive the corresponding actions over here. This is how you solve your reinforcement learning with deep learning architecture. Then you have to understand why we have to use this, why we have to go through this procedure. The reason why we have to go this procedure is that our conventional Markov decision process or Q-learning takes a lot of computation because they are fundamentally based on the dynamic programming, as we introduced before. Previously, I told you that we are fundamentally based on the dynamic programming. Since we are fundamentally based on the dynamic programming, we have a lot of computation cost over there. It takes pseudo polynomial time computation. That's why when we have larger and larger state, then we cannot solve the problem in a given time. That's why here we are doing some approximation. Once we are done for the training, even though it takes a lot of time, once we found all the parameters here, then when we have one state, then we can derive our desired actions or approximated actions based on this trained data. That's why the computation should be much more faster than our deep dynamic programming based solutions. That's why we are using deep learning architecture for reinforcement learning. Okay. So any questions here? So we are studying about the DQN. DQN is very similar to our previous lecture. So we have neural network architecture. We put a lot of state here. We put a lot of Q values with the action mapping here. And then we find the maximum Q value here among this given n number of data set. And then we pick one action based on that. Okay. That is our Q network here. So based on these kinds of the architecture, we are saying that we are doing the Q function approximation. Then we can derive our result based on this neural network architecture. This is how you solve your given reinforcement learning problem with neural network architecture, okay? So this is your programming related stuff. So let me skip this one because this is a theory class, not for the programming itself. That's why let me skip this programming part. So we will gonna skip this programming and then we will go to the imitation learning, okay? Suppose that we have only one single neural network architecture and then we put state here, we put actions here, and we are going to train this neural network based on the given data. And then once we have some similar data S, then we can make a result as an action. Then that is called a deep learning based reinforcement learning. So we have to gather a lot of data to train this neural network architecture for reinforcement learning. That's why we are training a policy, reinforcement learning policy based on, in order to mimic the expert demonstration. That's why we need a lot of data from the expert. That is the main data gathering procedure for reinforcement learning computation procedure, okay? So in this left-hand side, you see the reinforcement learning computation procedure for given game data set here. And then once we are done for the training, these agents can work based on our previous trained data. That's why we can let them do the cooperation just like that. So this is fundamental purpose of the deep learning based reinforcement learning. Okay. So here, as you can see here, we gather a lot of state information and action information. The state is our minimap and screen map, and our action is selecting some unit and then drag to move to the other part. That's why our action will be select and drag. And based on these S and A, you will make a training data set at first. Based on this training data set, you're gonna train this one, policy pi. And then based on this given statement, you can derive your actions, okay? So autonomous driving as well. So in imitation learning, once you have some neural network architecture in a state, you can put a lot of sensor data, LiDAR sensor, millimeter wave sensor, a lot of sensing data are existing in autonomous driving, and your result will be your action space. That will be steering wheel and brake pushing or something like that. So these will be your actions for the autonomous driving, okay? So in these medical applications, your state will be blood pressure and BIS and something like that. And then your action is the injection of these kinds of the medicine. So injection control will be done, can be done with these kinds of the imitation learning in order to mimic this exponent demonstration. Okay. And then now we have to move to the multi-agent reinforcement learning, and then we can go to the applications about that. Okay, so now we are in 320. If you have any questions for our previous topic, please let me know. Then I can introduce the result one by one. Okay. So this is 320. So please leave your questions in our chatting box, and then I can reply to you one by one. And then we will gonna start the other classes from 3:30. So for 10 minutes, please leave your message or your questions in our chatting box. Then after 10 minutes, 3:30, I'm gonna answer one by one, and then I will move to this autonomous mobility applications from the time. Okay, so you have 10-minute break. During the 10 minutes, if you have any questions, please leave your message. Thank you. Okay, let's start the class now. But before starting, let me have just 1 minute to forward one email to my graduate students. I need to send an email to them, forward an email to them. That's why let me have just 1 minute, please. So here. So let's start. So our last part, the autonomous mobility of applications, okay? But before starting, we need to understand multi-agent reinforcement learning. So here you have agent 1 and agent 2. But if they are not cooperating or they are not talk to each other, then it means that they will gonna work separately, independently. Okay, then they will work similarly because they have some same environment, they have same reward function, they have same action space, then their action taking would be the same to each other, then they will gonna work same at the same time, similarly. But this is not what we want. We want to let them cooperate and let them work separately and then make an ultimate goal. So that is our main purpose for multi-agent reinforcement learning. That's why we want to let them do the cooperation and correlation. Then in order to do so, they will gonna make individual state at first, and then they will be trained in a single neural network, then their information will be mixed together. And then eventually we will gonna derive two actions here. The first one is the action from the agent 1, and second one is the action for the agent 2. So this is the multi-agent reinforcement learning's basic concept, okay? So this is called CTDE. What is the CTD? Centralized training and distributed execution. So that is called CTD because they are trained in a single neural network. That's why they trained it at the same time in a single neural network. That's why they are trained centrally, but their neural network will be distributed to individual agents, and they will gonna make an inference for the others for their own actions. That's why they will gonna do the execution distributedly. That's why they are saying that this is a CTD, centralized training and distributed execution. Okay. And based on that, how we can do that? We can explain this one in a single illustration, not this complicated formula. I can introduce this one in a single neural network example. Okay. So suppose that we have 4 agents. This is first agent, this is second agent, this is third agent, this is fourth agent. It means that you have 4 different agents here. This is the hidden variable for the first one, okay? And then we define new variable that is called a communication variable. So communication variable means that I wanna see the other agent information. That's why communication variable here can be calculated as the mean operation for the others. For the others, we will take the average of them. That's why we have mean operation here. So here, based on this concept of the communication variable concept, we can make this illustration. So this is the first agent, second agent, third agent, and fourth agent. For the first agent, this is a hidden variable. The communication variable can be obtained by this one, and this one. Okay. For the second agent here, its own variables is here, but for the communication variable, it can be calculated by this one, and this one. For the third one, this is its own data, but the C sub 3, the communication variable of the agent 3 can be calculated by the mean operation by this one, and this one. Everything except myself, okay? The last one here, the fourth one, this own value is here, but its communication variable can be computed as a mean operation of the others, this one, and this one, and this one. And then you got this one, right? So for individual agent 1, 2, 3, 4, they have a hidden variable and communication variable. They can be mixed together. And then they can go through the activation function, and then that can be the hidden variable for the next layer. And then we will walk through this hidden layer computation 6 times or 8 times, then we can mix all the information all together. That's why we can do the correlation and cooperation. Okay, we can make the correlation and cooperation. So here, this is called ComNet because this is a communication network. That's why this is called ComNet. So in this ComNet, all the hidden variables are identical and homogeneous. That's why they can work together. They can make a same correlation altogether. But in the next page, when you look at this one, you can make the relationship of individual agent as a graph. So in here, the second agent and fourth agent, they have no arrows at all. Then it means that they have no correlation at all. But when you look at this one, the second agent make impact to the third agent make an impact to the first one and fourth one. The first agent can make the impact to the second one and so forth. These kinds of the relationship can be defined as follows, okay? So how we can solve this one? This is a heterogeneous type of the multi-agent cooperation. So for this purpose, so first of all, we have to define the graph at first for the, and then in order to define the graph, we have to make edges at first with hard attention, and then we can put the weight vectors for on top of the edges. That is called soft attention. That's why here, as you can see here, in order to define the graph, you are doing the edge definition and then edge weight definition. That's why you have these kinds of the learning procedure, okay? So this is two-stage learning procedure for hard attention and soft attention. So how we can do that? For the first one, you have to define this graph all together. That's why, real world data and the, real world action, you are doing the encoding and decoding in order to derive, in order to make a mathematical structure inside here. For inside here, you are doing the hard attention and soft attention. For the hard attention, you derive your edges and graph. For the soft attention, you define the weight factors on top of the edges. So these are your G2ANet architecture for heterogeneous computing, okay? So here, for the first part, you just define your agent and that's it by doing some encoding. And then for the second part, you are doing the hard attention. Based on this hard attention, you just make a adjacent matrix in order to make a relationship for the edges. So as you can see here, 1 is sending signal to 2. So 1 is sending to 2, that's why it is 1. 2 is sending 4, that's why this is 1, because this is 2, 4. And 3 is sending to 4 as well, that's why 3 is 4, sending signal to 4. That's why this is also 1. This is 3, 4. The others are all 0 because there is no edges on top of that, okay? And then this is called edge definition, okay? And then with the soft attention, what we have to do, we have to calculate the weight factors on top of the edges. That's why we have this one. This is the result of the soft attention. And then right after that, you define the matrix for the hard attention. You define the matrix for the soft attention. You are doing the element-wise operation. Then the 1 is multiplied with this one. That's why it is existing. And 0 is multiplied with this one. That's why it is 0. So only the part where you are in 1, and then your values will be existing. So your value 0.11, 0.72, 0.28 will be existing here as well. Okay. That's why you define the edge. You define the cost over there, right? So this is the hard attention and soft attention procedure in order to define your graph, in order to define your weight factors on top of that. Then you can make a separated and customized relationship among these given agents. That is our main purpose in order to use G2ANet, okay? So lastly, let me show you some examples about that. So applications, electric vehicle charging. So this paper was when I was in Chungang University, maybe 2 years ago, 3 years ago, I wrote this paper with Professor Daeyeon Choi, so who is a Chungang University professor in electrical engineering. This guy was my master's student at Chungang, and then it was published in Transactions on Industrial Informatics 2020 May. So at the time, we solved a problem to do some multi-agent reinforcement learning for scheduling problems for charging for electric vehicles. So we have charging stations over there. So they are all the agents. They can do cooperation and coordination in order to share the energy values. By sharing the energy, we can minimize the purchase from outside. Then we can make an energy efficient or economic system in order to provide energy sources to electric vehicle, as well as we can minimize our purchase from outside the utility company. Then we can make economic design. Now this paper was talking for that, and we are using multi-agent deep reinforcement learning for agent training over there. But here we don't need to say that. We don't need to say that individual charging stations are heterogeneous. That's why we just assume that all the agents are homogeneous. That's why we just use the ComNet at the time. Next slide is multi-UAV charging problem. This is with Professor Jaeyoung Kim at Aju University, Dr. So Hee-jung at Aju University. With the team members, we solved this problem. So this is very similar to our previous one. This was published in IEEE Transactions on Vehicular Technology 2021 June last year. And we have multiple UAVs flying, and they should be charged because they can be power hungry. Their lifetime might be 1 hour, 1.5 hours, and so forth. That's why we need some charging scheduling over there. That's why these UAVs should be charged over wireless. That's why we have to make a scheduling problem, and then we have to provide energy sources to the UAVs, and then we have to facilitate the energy sharing among them in order to minimize the energy purchasing from outside the utility company. So that's why we have neural network architectures. We have state information for individual charging stations, and we can derive the actions about that. Okay. And then we have another problem that is called UAV surveillance. It was published in IEEE Transactions on Information, Industry Informatics. It will be published in this year, October session. And this was by our student, PhD students over there. And then we used the surveillance problems. We used the ComNet into the surveillance problem. So multiple UAVs are flying over there, and they are flying here and here, and then they will do the surveillance in the given network. And then we have to make a positions for individual drones, and then we have drone coordination in order to control our actions in individual agent. So here the UAVs are agent, okay? So for that purpose, we do not need to assume that individual UAVs are all heterogeneous. That's why we just use the ComNet architecture, okay? So this one is the streaming in connected vehicles. So here you can see several vehicles, they are moving around, and then we set the beams to the individual vehicles, and we can do some downstreaming for the video contents. For that purpose, this was published in 2022, February this year. And then this paper, in this case, our action is the distribution of the video contents, and then we can control the video compression ratio as well. So that was for the seamless video service providing in moving connected vehicles. This paper also some mathematical analysis with Markov chains. That's why we have these kinds of the mathematical procedure. And then we have drone taxi trajectory. We have some drone taxi applications, and taxis are moving around. And then if they are a single agent reinforcement learning, their action might be almost the same to each other. That's why they are moving around. Similarly, for these given four agent, however, when we are using the multi-agent deep reinforcement learning, they can move around all over the network separately and distributively. That's why we can, its performance is much better than the right-hand side. In addition to that, depending on the positions for individual drone taxis, their trajectory can be different, because some part we have a lot of people over there, some part we have no people over there. That's why we need to define heterogeneous type of the path. That's why we are using the G2ANet for this application. So up to now, we reviewed all the basic examples or samples for the reinforcement learning. So if you have any questions, please let me know. This is the end of class today, okay? If you have no questions, then you can leave now, or you can ask any kinds of questions for me. No questions? If you do not have any questions, then let me finish our class here. So I just distributed our assignment template. That's why you can refer to the template for your assignment. In terms of the summary, you have to submit all the summary note by the end of Saturday. So by the end of Saturday, please submit your assignment by the time, okay? So summary, yes, Julius, any questions about the summary? Let me know, then I can answer to you. Is there any audio recording need? Audio recording? No. Audio recording. There is paper presentation. So tonight I will gonna post again for the paper selection. And then once your turn is arriving, once your turn is coming, then you need to record and you need to send it to me or you need to post it. Okay, but not now. Okay, you don't need to worry about that. Not now. I will post the guideline by tonight or today morning. Okay, thank you. Any questions more? So Julius, you can see the what? How many pages should the summary be? So I just make 2 pages. Did you see that in the PowerPoint template? I can show you here. So here, this is template what I shared today. So here you need to put your ID here. You need to put your name here. You need to write down your paper title. You need to write down your summary here. Only 1 page here. And then you have to write down the past plus advantages of the proposed algorithm. What is the cons? This is cons, okay? What is the disadvantage of your that algorithm? Then you have to write down 1 page and that's it. So for individual recording, you have to make 2 pages. So you have to make this one for 2 presentation. That's why entirely you need 4 pages to submit. Do you understand that? Noted. Great. Thank you so much for your attention. Thank you. And ask any kinds of questions if you have in our Kakao Open chatting room. Then I can answer to you. Okay. Okay. Thank you very much and see you all together. Thank you. Thank you very much for all together and see you next time. Thank you.